Okay, now we will look at a slightly different problem, absolute mean and absolute max. So this word absolute is sometimes used for global. Okay, so if f, again we'll look at two variable functions. If f is defined on all of R2, then its global mean, when you talk about its global mean, it sounds good. But if f is restricted to some small set, then the word global sometimes gives the wrong idea. So we use the word absolute mean max, but both mean the same thing. That's the absolute minimum, the largest value of the function and the smallest value of the function restricted to a set. Okay, so here we will use the following idea which we did in the first few weeks of calculus last semester. So main tool is the following thing: a continuous function defined on a closed and bounded set attains its minimum and maximum. Minimum and maximum values at some points on the set. Okay, let me emphasize this. Okay, this is repeating at some points on the set to emphasize this. Okay, so here open and closed, bounded and closed is required. So we have examples from one variable case. For example, the function 1 over x on the bounded interval 0 to 1, where 0 is excluded, is not going to have its maximum there. It is unbounded there because the set is not closed. You remove one endpoint on the interval. Now it's not closed. Okay, but the function 1 over x is bounded on any interval which doesn't any closed and bounded interval which doesn't involve 0. Okay, so we showed this. The reason why we showed this without using x and y, only using continuous function, is that now we can apply it in several variables also. So we will be applying this for two variable functions. So mostly we will be interested in two variable functions. Now, if a continuous function is given on a closed and bounded set, we know its minimum and maximum exists. How do we find it? Okay, in general, if the function is really continuous and has no derivatives anywhere, such functions exist, continuous everywhere, but the derivative does not exist anywhere, then the only way to find its minima and maxima is by approximating the function, plotting the function, trying to guess where the minima and maxima occurs, and you get some numerical approximations. If the function is given by some formulas, the chances are that the derivative fails to exist only on some subsets, but most of the time the function has derivatives, so the techniques of calculus can be applied. In our case, we will look at functions of two variables which are C2. So the derivatives exist, the second derivatives exist, and even the second derivatives are continuous. So we will see how to apply this idea with the techniques we learned so far. Okay? So the problem we are interested in is now the following. Let f be a C2 function. Remember that this means the second derivatives are continuous. So this is required to apply the second derivative test. Remember, in proving the second derivative test, we explicitly use that the derivative with respect to xy is the same as the derivative with respect to yx. So that when it is C2, when the function is C2, it is guaranteed. Defined on a closed and bounded set D in R2. So if the function can be cooked up nicely, we can also do this in R3. But you see that you will see after we do this that the calculations will be very lengthy. but the idea will be the same. Okay? It is now guaranteed that a minimum and maximum exists. So the question is, find the min and max of f on D. Okay, so these are called global min or absolute min or max points. Okay, so that's the terminology. Okay, so here is the procedure to do this. We find the critical points, but here you see, just like in one-dimensional case, we have to consider what happens at the boundary also. Okay, so you can convince yourself easily that boundary matters, because suppose D is the unit disk in the plane, and your function is linear, so it's just a plane going like this. So you see, obviously, the minimum value and the maximum value of this plane cannot occur at an interior point. Okay? So it must occur somewhere here, minimum point, and maximum must occur somewhere here, and it has nothing to do with the derivative inside the disk. Okay? Okay, so how to find this? How to find absolute min max for this f on D. Okay, so here the idea is to find candidates for minima and maxima. There will be finitely many candidates for minima and maxima, if we are lucky, if the function is nice. So we don't try to attempt to apply the second derivative test. We just find candidates, and at those candidates, after we find all the candidates, we evaluate the function. Okay, calculus now guarantees us that the smallest number we find is actually the smallest value of the function over all of D, and the largest of these finite many numbers is actually the maximum of the function on all of D. Okay, so what are those candidates? So first, find those critical points of f which lie in D. Actually, in interior of D, in D minus boundary D. Okay, so let me do this. Here, boundary D denotes the boundary of D. Again, if D is arbitrary, finding the boundary of D is, again, a total problem in itself, but we will be using simple sets. Simplest set is circle, so the boundary is a simple set. D will be a disk, boundary will be a circle. We will be using triangles, so boundary will be 3 pieces of straight lines. Okay, and if we are mad at you, we'll say make D a rectangle, so you'll use 4 boundary points. Okay, so first we take the critical points of f which lie at the interior of D. This is called the interior of D. We are not looking at boundary of D because we'll treat boundary of D separately, and this critical point will show up there anyway. Okay, so here let's say P1, P2, generally in our case we'll have 1, Pn critical points of f in D, D minus boundary D. Okay, to restrict f to boundary of D. Okay, so this is a curve. This is a curve. Okay, so remember that this curve follows from the condition that we are working in R2. So if you have a nice region, its boundary is a curve. If this is going to be a problem solvable by hand, so you should be able to parameterize the curve easily. This is a curve parameterized by t in some closed and bounded interval. Okay? So find, so let's see, we say, so let phi of t be f restricted to boundary of D with parameterization parameter t in A, B. Okay, so we reduced the problem to one-dimensional case. Now we remember how we did this. We find the critical points of this inside AB. Okay, find critical points of phi of t for t inside A, B. Let Q1, Qm be the corresponding points on boundary of D. Okay, and 3 also consider R1 and R2 on boundary of D corresponding to T equals A and T equals B. Okay, so this part you may have to repeat this. Repeat this if boundary of D is a union of several curves. Okay, so for each curve, so for example, if it's a triangle, there are 3 straight lines as the boundary. On each straight line, you have such a setup. Okay, so you parameterize the curve, in that case, a straight line. Okay, you find the critical points, if any, inside the interval, and then you add the endpoints. Okay, so you have a list. So finally, after you do this, finally, you evaluate f at the above points. Okay, so f of p1, f of pn, f of q1, f of qn, f of r1, f of r2, and if you repeated these, then this part will have another list here. Okay, now calculus tells us that you have only finitely many points here. There is a maximum and there is a minimum. So those numbers are the global minimum and maximum of f. The smallest of these numbers is absolute minimum of f on D, and the largest of these numbers is the absolute maximum of f on D. Okay, so that's the procedure. So you see that now we totally understand how this works, why it works. It's just that now it takes a long time to go over all of these things, in particular when the boundary of D is a union of several curves. So let's do one example that is common in all sections. Okay, so I'll do this example that you see on Moodle. Then there is an exercise here. I'll also solve this exercise. So let's see. Okay, now the problem here, first problem here, find the absolute min and max of f x y, which is x cubed minus xy plus y squared minus x on the triangle D, which is x, y in R2 such that x and y are positive and they add up to something not larger than 2. Okay? So this is the problem. So it always helps to draw a picture because you see at this part, for this part you don't need the picture because you'll just find critical points and check if they are inside D or not. But for this part it helps to draw the picture because you are going to parameterize the curve. You have to see what the curve you are going to parameterize. X, y. So this is 2, 2, 0, 0, 2, and 0, 0. So this is the region with the boundary. This is D. Okay. So we'll find the critical points of F. So since this exercise to demonstrate the ideas here, one of the critical points must be outside, one of them must be inside. We will just take the one inside and list it here. Okay. Then here you see we have 3 pieces for the boundary. We'll parameterize this line, which is easy. You'll restrict the function here. Now it will be a one variable function. You'll take its derivative and see if it vanishes somewhere here. If it does, you'll take that point. And then you'll also take this point and this point because these are endpoints. Okay? So this procedure for that part is finished like that. Then you do this and you do this. Of course, you don't have to take this point twice because this is the boundary point of this line and also this line. You only need to know that this point, and this point will be in the list. And the function restricted to this line, or to this line may have its derivative vanishing somewhere on the lines. You'll take those points. Then we'll evaluate them. Okay, so let's see how that goes. So first find the critical points on the interior of D. So interior of D is x and y are strictly positive, x plus y is strictly less than 2. Okay, so we have fx equals 3, x squared minus y minus 1 equals 0, fy equals minus x plus 2y equals 0. So, okay, we'll solve this. Let me skip. Since this is given on the Moodle, okay, so I'm just explaining how this works. So we have 2 points, 2 critical points. So one of them is 2 over 3, 1 over 3. This is inside D, interior of D. So sometimes we do this notation to say to denote the interior. Sometimes you just write interior, okay? As long as what you are doing is clear, it works. And the other one is minus 1 over 2, minus 1 over 4. You see, this is not in D at all because xy must be positive. So this was 4, okay? So we take only this one. So we put only this point in our list. Okay, so when you are doing yourself, it helps to put these things into a box so that later on, when you go through your calculations, you don't try to check where the points in the list was. Okay, so you immediately see that the points in your list are boxed. Okay, so now we put this, and later we'll evaluate the function there. Okay, so the next thing is now we parameterize the boundary of this. The next step is to restrict F to boundary of D. Okay, so there are several points on the boundary. So okay, let me continue here. Okay, so boundary of D consists of three line segments. Generally, we use the word segment to denote that it is bounded. Okay, so side 1. So let me see which one we started here. Side 1 is, okay, so let's do this here. This is side 1, okay, when y is equal to 0. Okay, side 2 is this side. Okay, so this is side 2. And this is side 3. Okay, so side 1 is y equals 0 and x is between 2 and 0. Okay, so you see x already parameterizes this side. So here phi of x is f restricted to this part. X I use as a parameter, y is 0. So when you put y equals 0, you have x cubed minus x. And x is between 0 and 2. Okay? So this is the function we want to maximize or minimize on this interval. So we take its derivative and find the critical points. Phi prime x. I'll do this in detail, and then I'll just write the results of the other sides. So this is 3x squared minus 1. I want this to be 0. So x squared is equal to 1 over 3. And x is equal to 1 over 3, or x equals minus 1 over square root 3. But this is not in 0, 2, so I throw that out. Okay, so this is in 0, 2. So actually here I want the open set, so let's be pedantic and say that we are throwing anything that's not inside. Okay, so the point contributed here is x equals 1 over square root 3 and y is 0. Okay, so square root 3. Okay, so we also take this into a box. And what was the other step? Find the endpoints. Find the points corresponding to the endpoints of your parameter. Okay, so endpoints of our parameter was x. It will give me this point and this point. Endpoints are 0, 0, and 2, 0. So I also put them in boxes. Okay, so for the others, I'll just write the results. Side 2. Okay, here x equals 0. Now y has to be between 0 and 2. So I use y as my parameter. So I can have phi y equals f of 0 y. When x equals 0, this is y squared. And y is in 0, 2. Okay, so you see you take its derivative. Its derivative does not vanish on the interior. You take the endpoints. Endpoints are 0, 0, and this one. This already is considered in the previous case. This is the new point. So endpoints. So here y prime y is not 0 on 0, 2. Okay, it's 0 at 0, but the 0 will be considered as an endpoint anyway. So endpoints, new endpoint is 0, 2. Okay? So I make a remark here, 0, 0 was considered before and already added to the list. Okay, so this is our new point. So the other part, okay, let me do that part here, psi 3. Okay, so here we have x plus y less than or equal to 2, and it's positive, and x and y positive. No, this is, they are equal. Okay, so the equation of that straight line is x plus y equals 2, and I can solve one of them in terms of the other. Let's say here y is equal to 2 minus x. Now I have to decide where x is. Remember that that's why we draw those pictures. X is between 0 and 2. So x is between 0 and 2. Okay? So my function phi x is going to be f of x 2 minus x. Okay, so I just write this from there. X cubed minus x times y, x times 2 minus x, plus y square plus 2 minus x square minus x. This is my function. Let me see if it is simplified here. Okay, so this is equal to x cubed plus 2x squared minus 7x plus 4, and x is in between 0, 2. Okay. So phi prime x equals 0 when x equals, I'm not calculating, just writing from here, x equals 1 or x equals minus 7 over 3. So this is not in the interval. So we throw that out. Okay. So corresponding to this, we have the point. Okay, x equals 1, y equals 1. Okay. And the endpoints, but the endpoints are already considered before. So the endpoints are already included before. So we don't have any new contribution from this side. The only contribution this side gives is this number. Okay? So now you see we have this 5 points, which are candidates for minima and maxima. All we have to do is evaluate the function at these 5 points. I have another one here. So where shall I do that? Okay, so let me do it over here. Evaluate f at these selected points. So let me see where f of this one, 2 over 3, 1 over 3 is calculated to be minus 13 over 27. And here we have 1 over cube 3, square root 3. 1 over square root 3, 0 is calculated to be minus 2 over 3 square root 3. And then I'll do the endpoints, but we have another critical point, nice point there. So f(1,1) is 0. Now we calculate the endpoints. Okay, so f of 0, 0, f of 2, 0, f of 0, 2. So let me see what those things are. 2, 0 is 6, 0, 2, 0 is 6, 0, 2 is 4, and 0, 0 is 0. Okay, so the smallest of these is the minimum. Okay, so smallest of these is, okay, so which one is smallest? Okay. it turns out that this one, okay, you have to calculate, is minus 13 over 27, which is approximately minus half. Okay, so this is less than that. Well, the absolute value of this is less than that, so minus is larger, which is the global, which is the absolute or global mean of F on D. The largest is easier. Okay, let's write D here. The largest of these is 6, clearly, which is the absolute max of F on D. Okay. Okay, so the minimum occurs somewhere inside, okay, and the maximum occurred at this point. Okay, so this is the demonstration of the technique in finding absolute min max on a closed and bounded set. The idea is simple, but depending on how complicated the boundary is, you have to do several calculations over and over again. Okay, there is an exercise coming after this in the handout. So let me attempt to solve that problem. It looks like this is simpler because there is just one boundary complement. The boundary is a circle, but you parameterize a circle by trigonometric functions, and then it's not easy to find minima and maxima if the function is not very special. In our case, the function is nice, so we will be able to solve it. That's why it's an exercise. You can solve it. Okay, so the exercise says find the absolute mean and max of f x y, which is x squared plus y squared minus 1 squared plus xy on the unit disk d equals xy in R2 such that x squared plus y squared is less than or equal to 1. Okay. So the procedure is the same. We'll find critical points, pick up the ones that are inside the disk without the boundary, and then we'll restrict the function to the boundary. In the boundary, it's going to be a little bit, the function is easy, so it will be easy on the boundary because you see on the boundary, x squared plus y squared is 1. So this part is 0. On the boundary, this is just xy. We'll try to find the minima and maxima of xy. It's going to be easy. And then we'll have those, we'll have 4 or 5 points. We'll evaluate the function at those 4 or 5 points and decide which one is smallest, which one is largest. Okay, so I did some of the calculations here, if I can find my notes. Okay, so first find critical points. In the interior. Okay, so for this thing, you see I take fx equals 2x squared plus y squared minus 1 times 2x, okay, plus y equals 0, and fy, so it's the same thing, it's going to be 4x squared plus y squared minus 1y plus x equals 0. Okay, so here, first of all, x 0, 0, 0, 0 is a critical point. Okay, so obvious. Also note that x equals 0 here, if you take x equals 0, y is 0. If you take y equals 0, then from here it forces x 0. So x equals 0 if and only if y equals 0. So if there are any other critical points, neither x nor y component will be 0. Okay? Now to find other components, to find other critical points. Okay, so what do you suggest we do? Huh? Subtract what? Well, you see this one is, maybe I rewrite this. This is as 4x plus y. So when you subtract them, you'll get, okay, let's do what you say, fx minus fy. So we have 4x squared plus y squared minus 1x minus 4x squared plus y squared minus 1y plus y minus x. So maybe you want this out, 4x squared plus y squared minus 1, x minus y. Let me also make this x minus y. Then I have x minus y, 4x squared plus y squared minus 1, minus 1. So we find here that, okay, so I'll put dot, dot, dot. You do things, and what you find here is that either x equals y or x equals minus y. Okay? And x equals minus y. Here, x equals minus y will not come out, but something else will come out. Okay, so let me just write the critical points then. Okay? The way I did was to observe the symmetry. So I multiplied this by y. Okay? Here I have y squared, here I have xy. Then I multiply this by x because I know that x and y are different than 0, so I can multiply and divide. Then I subtract. After I subtract, you see that these parts cancel. Then you have x squared equals y squared. So either x equals y or x equals minus y. One of them gives you a critical point, the other doesn't. Okay, so let me write the critical points. So other critical points. So first you have I have square root 5 over 8 and square root 5 over 8. So these are if this comes with different sign, plus or minus. So somehow I decided that this wasn't not in the disk, so not in the disk, not in D. If you add the squares of these, okay, what do you get? You get 10 over 8, which is not in the unit disk. Okay. Then the other ones are plus or minus 3 over 8 square root plus or minus 3 over 8. So in the interior, in fact. You add the squares, you get 3 over 8, which is less than 1. So these 2 points are inside the disk. So this one we choose, and this one. Okay. From the inside, we have this. So the next part is, in general, the tricky part when you are working with the circle, but in our case, the function is so nicely cooked up that we won't have much trouble. Okay. So next, we restrict f to the boundary. Okay, so we thought before we pass there, so I think that's all the critical points. This is the discriminant. I calculated. We don't need this, but just to understand what is happening, I applied the second derivatives here, and it turned out that these 2 points are saddle points. But at this point, we don't need that information. You do this just when you feel masochistic. Okay, so on the boundary, parameterize boundary of D as x equals cosine theta, y equals sine theta, and theta is in, say, 0 to pi. Okay. So f of theta, f restricted to boundary of D becomes f of theta, and this is just sine theta cos theta. Okay. On the boundary, this is 0, so your function is just x times y. That's sine times cosine theta. Just to make life easier or difficult, it depends on where you feel yourself comfortable. I write this as 1 over 2 sine 2 theta. Okay? So remember that theta is in 0 to pi. Okay? Now we find the critical points of this on the boundary. F prime theta is equal to cosine 2 theta, right? Now we want to find where this is equal to 0 when theta is, okay, so I did this. Theta is at pi over 4. So you add pi over 2, that is 3 pi over 4, 5 pi over 4, and 7 pi over 4. So on the disk, so these are the points. Okay, so you can either do this algebraically or you look at this thing and find where it is 0. Okay, so these are the points. Okay, so okay, so these are the points. Well, actually, I already have the function here, so I calculate. I don't need in this case to write the Cartesian coordinates for this because the value of the function is known. So these are the things that I will calculate here. Okay. So now in the final step, we calculate the values here. In the final step, we calculate the values of f at the chosen points. Okay, so these points are, remember, 1 over square root 2, 1 over square root 2, and different signs. But I don't need to do that here because I already have an expression of f in terms of theta, and I'll immediately be able to calculate the value of f at these points. So that's why I stopped there. Okay, now I have this point, first of all, f at plus or minus square root 3 over 8. Square root 3 over 8 plus or minus square root 3 over 8. Either I choose the plus signs or minus signs will not make any difference because here inside I'm taking squares anyway, and here I'm multiplying them with each other. Since they are going to have the same sign, the product will again be positive, so the value will not change when I change signs here at the same time. So I calculate this, and the number is 7 over 16. Then I calculate the value of f at these points. But the value of f at these points is easy, okay, because it's either, you see, if I have this twice theta is here, f is equal to 1 here, or 1 over 2, okay. F pi over 4 is 1 over 2, okay. And f 3 pi over 4 is minus 1 over 2. So the others will be again from here. I know that the others will be either again 1 over 2 or minus 1 over 2. Okay. So from here, minimum of f on D is, okay, you see it is this one, the smallest one, minus 1 over 2. Maximum of f on d is, well, you see this is less than half, this is half, so 1 over 2. Okay. We missed one critical point. Okay, so this is, we missed this one. F of 0, 0. So when we put 0, 0, we get 1, right? We get 1. So it turns out that I have to change my conclusion. Okay, so this is 1. So the maximum is now 1. Okay. So that's why you see I preached you that you put the chosen points in red, but even after that I missed that red box there. Okay, so this is the procedure. You pick those distinguished points and then evaluate the function at those distinguished points. The minimum gives you the absolute mean, the maximum gives you the absolute maximum. Okay, so that's all for today.